Yeah. 1 minute, okay. I'll filibuster a little bit more. Filibuster the State of the Union, make sure that no vote on anything important takes place, stuff like that. Good? Okay. All right. So is auditing C and C++ different nowadays? First of all, who am I? My name is Jared Demott. I've been doing security research for about 13 years. Fuzzing, source code auditing, reverse engineering, exploit development. Those have been kind of the 4 skills that somehow I decided years ago that I wasn't as good at as I wanted to be. And so I wanted to learn to grow in those 4 domains, okay? And if you're any kind of code auditor, developer, security researcher, hacker, whatever, those are the 4 domains that I think are sort of important that I try to stay current on and stay up to date. And so this is one of those 4, and that's why I'm giving this talk. I always try to give a training or a talk on something that I know that I need to learn more about too. So that's kind of usually my motivation for why I want to get up and talk. So the answer to the question of, is it different? And the answer is, yeah, but not always, just depending. So in terms of background, that's what I'll cover first in the talk today. So the talk will be split up into 2 main, categories. You'll have what the state of code was, and kind of where it is now. So it was memory corruption with simple API misuses and things like that. We'll look at some examples. And it now, the bugs you're seeing in C and C++ code are more of the use after free and the type confusion and stuff like that. And that's kind of what we'll talk about toward the end of the talk. So I'm just going to jump right into it. Try not to trip on the cord here. And keep going. Okay, so older bugs first, although they may not be older bugs if you're involved in any sort of SCADA, medical, automotive, legacy code, embedded code, anything like that. The bugs of yesteryear are the bugs of today. Okay, so these examples I have are kind of the bugs of yesteryear, although they might be for today for you, depending on your domain. So what are we talking about? Stack corruption, heap corruption, global variable, misused format strings, misused APIs, complex loops, string conversions. And don't forget the 3 primitives you need to land a successful exploit are either the read, write, or the execute. So those are kind of the 3 things that you'll be looking to somehow corrupt, control, influence, hijack, whatever. Okay, so the way I do this, and these are from the class I teach, these simple examples, is we just look at the first two lines of code. And does anybody know the first 2 lines? Is that a problem or not? Does it look okay? Looks, no. So what do we have? Char buff is a local variable, right? Buff is 1024 bytes on the stack. So I don't have time to go all the way through, calling conventions in x86 and the way that stack frames get set up and torn down when it functions, call and exit and all that kind of stuff. You can learn more about that in my class or other classes that people teach around the industry on this sort of thing. But basically this is going to be a stack, and the answer of whether it's a problem or not is we really don't know, right? So the way sprintf works, it's like printf, but instead of printing a standard out, we print to a buffer, right? So you're going to print maybe like jared.demott@bromium.com or whatever the name and domain is, but the thing is we don't really know how big name and domain are, right? And so the reason that code like this is problematic is that maybe somewhere earlier in the code they checked to make sure that those links were okay. Maybe they didn't. Okay, so it's very hard to tell at any snippet in time whether or not there's a problem. So in general, it'd be better if, in this case, they used snprintf or some other function that you can tell just by looking at this snippet that, yeah, it's safe or no, it's not. That way you don't have to go back in some big code database and try to figure out, is this really a problem or not, right? And you could put in a trouble ticket and try to get the devs to fix it, even if it's not, just by the fact. Okay, so the next one, I already put the answer up, is the next 3 lines is what's called an off by 1. So what we have there is we have this for loop copying bytes from some input into buff. And the problem is the fact that I is less than or equal to. It should just be less than, right? So 0 to 99 would be 100 bytes. What about the next one? malloc 100. Malloc is for the heap, right? So we're setting aside 100 bytes on the heap, and we're doing stir-in copy, which is the safe version of stir copy. So it should be good, right? No problem there. Except If you know anything about these parameters, if you don't know how the APIs work, you can just go to Google and type man space stir and copyright, and you can learn about that specific function if you're not sure how it works. But 3 parameters are destination, source, and length. And the length in this case is stirlen of argv1, which is argv, in the case of these simple examples, is basically considered malicious input, right? So that's like argv1 in this case is the untrusted user input. And so we're saying however long that is, we'll copy into this buffer. So even though they use the stir-in copy, the safe version of the function, it's unsafe in the way that it's used, right? And you see that sort of thing fairly commonly where, developers are told that they have to use this set of safe functions, but you can still misuse them, generally speaking. Where there's a will, there's a way. And the last one, printf argv1, is an old style bug. It's what's called a printf, or print format bug, or format string exception, or there's all different kinds of names for it. But the fact is, they don't use a format string. So in sprintf, you see that there was, in quotes, there was what's called a format string. So down here, if we're going to print, some name or whatever it is we want to print, an integer or a string or whatever, we should have some format string specifying how we're going to print that. Otherwise, the attacker gets to specify the format string, which they could do all kinds of interesting things with, right? They could specify a bunch of %x's, which would allow them to pop an arbitrary number of integers off the stack, right? So it could be an info leak. If there's a %n, they could actually write into memory, even though the %n's generally been nixed by MSDN and other popular compilers and things like that. So it's an old bug, but it still shows up now and again, especially in legacy code, embedded code, places where code maturity hasn't reached the same point that desktop maturity is, right? Okay, so this next one is if u short 1 is greater than -1, do I print or not? So the question is, does that print or not? Well, you would think so, right? Because 1's greater than -1, generally speaking. Although there's some sort of conversion taking place there, right? So a -1 is actually an integer, and a u short is an unsigned short, which is 16 bits or 2 bytes instead of 4 bytes, right? So the compiler is going to automatically do a type conversion there for you. And the question is, what types does it convert to? If it converts them both to an unsigned integer, then actually -1 would be bigger, and that wouldn't print, right? Because -1 would be FFFFFF, something like that. But if it converts them both to an integer, which is what it does, then 1 is still greater than -1. And so that's what happens in this case. It's okay. It converts it both to an integer, because integer can hold the size of unsigned short. But it's kind of one of those things where there's a ton of gotchas in C and C++. There's all kinds of little things where it's like, geez, I don't know what it does here. So you can write a little sample program, or you can do whatever you need to do to try to figure out what takes place in that case. Okay, this next one, what's the type of bug I'm trying to highlight here? Does anybody know what the bug here is? BOF 100, convert the first untrusted input to an integer and check to see if it's less than 100. So if it's negative, yeah, that's right. So you have some integer error, right? So if the input is a -1, -1's less than 100, -1's also a really big number. So when the stir-in copy takes place, the length will be treated as an unsigned int, so you'll have a really big copy into a small buffer. So pretty classic, pretty typical, pretty old school. So this is kind of, like I said, this is the background of where the state of, bug hunting in C was. And hopefully these types of bugs are not as common nowadays if you're still writing code. And so this snippet down here attempts to fix that basically by doing a stirlen. So instead of trusting the size of some input, it actually counts the number of bytes with stirlen, right? So you're going to count however many bytes are in argv1, and that's better as long as argv1 isn't null, and it doesn't crash in the stirlen. Then that should be fine because it's gonna do a better thing there. So stirlen is generally better. Some form of byte copying or counting is better than trusting a size, particularly if you're treating it as an int. Okay. Other examples of problems that have happened in the past. This is kind of an interesting one that I always thought was really goofy. If you use a lot of these MSDN APIs that deal with wide characters, which are 2 bytes, right, or tchars as they're called, you have to do size of divided by 2, basically. Size of buff 0 gives you the type of tchar, which is like 2 bytes. And it's really goofy because normally you would think that if you're setting aside 128 bytes, you could say copy whatever this, ID is into this buff destination, copy that size of buff. That should be fine, right? You're saying it's the size of buff, but size of returns bytes, so size of will return 128 times 2. And when it actually does the copy, it treats the number of elements that you want to copy as individual tchars. So it'll copy 128 too many bytes. So you have to basically divide your size of by 2 to get for it to do the right thing. So there's a lot of goofy things like that to look out for. And there's many different functions that have that exact same issue where you need to make sure you normalize your size. Okay, so those are some of the other, those are some of the bug types you might look for. Well, what are some of the techniques? And there's all different kinds of things I could talk about. We could talk about hunting for certain types of bugs or fuzzing or all different ways to find bugs. But one of the popular ways to find bugs out there is by using third-party libraries and differencing. And this could be some sort of patch differencing, or it could be, in this case, we're going to look at code, though, instead of binary. So this is some little example that I also have from my class. And the premise of this exercise is basically pretend you're a software developer and you're creating some browser or whatever it is, and you leverage some third-party product like OpenJPEG. And your boss wants you to use 1.4 because it's been tested, it works, and everything's happy with that. But you know that 1.5 is out, and you think, geez, shouldn't we use 1.5? And he says, no, because it hasn't been tested, it could cause regression problems, and we're ready to ship, and everything's really tight on the deadlines as usual and all that stuff, right? So you think, well, as a diligent, whatever, developer or security engineer, I'm just going to go and do a difference, basically, between the 1.5 code base and the 1.4, and look for some issues that may have come up. And you could difference the whole thing and then try to individually look at every difference, but there might be a lot. So you might also just do like a CV internet search and go, are there any problems with 1.4 that are critical that have been fixed in 1.5? And you go, oh yeah, there really are. And this is like actual real stuff, right, from OpenJPEG 1.4. These are bugs that were found and fixed. So you've got some code execs and some DOS overflow, all kinds of good stuff like that. Sometimes they're mislabeled, right? Sometimes it'll just say that it was a DOS when really maybe it was a code execution, things like that. So that happens occasionally. So you go, okay, I better look into one of these. So you grab a tool like SCI Understand. That's a tool I use a lot for looking at code, auditing code, and also for differencing code. It's really good for differencing code. So you put in the 1.4 project and the 1.5 source code trees, and you difference them, and you come up with a whole bunch of these places where they'll be like colored, where, here's the original and here's the changed. And in this case, this was one of those CVEs where there was, in this file called t2.c, there was one minor little change. You can see it on the very end there, where there was a size of unsigned char star versus a size of unsigned char. And we'll look at it again on the next slide. I just wanted to show you a picture of kind of the differencing engine in SCI. I kind of like it. I think it displays it nicely. And so the only difference between these two lines of code, between the critical code execution, ODE, and the everything's fine now, is 1 star, right? That's the only difference, and that's pretty typical, right? Things kind of get crazy, in terms of like, what was the critical issue here and what was the critical issue there, or whatever. In this case, it's just 1 star, and the difference is the size of unsigned char star is a pointer, which is 4 bytes, right? And the size of unsigned char is 1 byte. So there's a difference in the math that takes place in this OPJ realloc, which is some wrapper around realloc, okay? So they're allocating the size of some buffer based on some untrusted user input, which are the length and the new length, which you can specify, and then they multiply it by some number. So if you put in, for example, 8,000 hex or whatever, and you multiply it by 4, you end up with some small number, 4,000 hex. And normally that's fine, okay, as long as you do that same math in the copy. But the problem is, and this is a pattern I've seen before, and I'm sure it'll come up again, is where they do math in the allocation, but then when they go to do the copy, they don't do the same math. If they did the same math, everything would be fine, right? You'd end up with the same size for the same buffer. But when they do the copy, the mem copy it copies data plus len, and then C is like the input with this new len, which you could specify, which was 8,0,0,0,0 hex. So you've got some very big copy and some small buffer based on integer wrap type issue, okay? Because they didn't use the same math in different places. So that's something that the whole point of that example was to say that's something to look out for. That's something to audit closely, is the allocation routines and any questionable math that's being done in the allocation routines, and then later look at the copies that are near those and see if they use the same sort of math. Because it's pretty common that they'll do a lot of dynamic allocation, right? There'll be some math probably. Okay, and so if you wanted to, take it to the next step, which would be like the exploit development, exploits, as you know, are written in debuggers, right? So you got to fire this program up. You do windebug-hd, which is don't use the debug heap, -c, which is run this command, which is g, which just means go, don't stop in the initial user breakpoint. And then the program that you're testing, and then whatever malicious inputs that you have that cause your crash, you see that windebug fires up, and you see that there's an access violation, C0005, which is typical, memory write or read type access violation. And you look at the registers, which I don't know if you can really see very well from the back of the room, but you see that EAX is the square brackets. We're trying to move square brackets EAX plus C, which means dereference, and the value of EAX was 2790, 759A. So, and that points to some unmapped memory. So you've got some unmapped memory that we're trying to read from to write a value into EAX, which is what causes the access violation. So presumably, when we do that large copy, we're trying to read outside of the bounds of a mapped page, which is what's causing the access violation, okay? And so if you run bang exploitable, which we do at the end here, which is just some tool, if you haven't used it, that tries to guess at the exploitability of a crash, it says unknown, and generally that's because whenever you have a read access violation, it's basically a lot of times going to come back as unknown exploitability, because it doesn't really know, are you reading in some way that we could turn into a code execution hijack or whatever. As you know, write access violations are generally more favorable in terms of exploitation, so that would probably come back as probably exploitable. But this one, since it actually crashed on a read, you could probably change the flow so that it crashed on a write, and then it would give you a better result. So you kind of take that with a grain of salt when you look at that tool. It's very not perfect. And there's all kinds of other issues that you could go back if you take a class or read a book or anything on auditing C, and all the kinds of flaws that have been found throughout the years: null pointers, typos and variables, forgotten defaults in a case switch, uninitialized memory, incorrect pointer usage, returning a locally scoped pointer outside of a local, that can be a big issue, exception handling mistakes, time of check, time of use, which are kind of exciting. I'll mention one of those in a second. Unchecked return values, out-of-date compilers, which is big. Visual Studio, as you know, you should probably be using the most recent. If you're using a really old version of Visual Studio, it's probably not going to be doing the stack cookie and opting into ASLR and DEP and all the kind of modern protections that you really want your compiled code to opt into. So look for that. Ignored warnings, old STL for C++. Those are all the different kinds of issues that have happened in the past. So, okay. Closing the door on the past. That was kind of the stuff that, was a problem, might still be if you're working on legacy code, but what are some newer issues now for today? And we're going to generally be talking about, kernel code and browser code and C++, that kind of stuff. Because C and C++ really shouldn't be used for general use. You really shouldn't be using it, for writing, some basic tool or the cafeteria menu in this case or whatever. There's a lot of other safer languages out there to use, C#, whatever, that if you don't have to use C and C++, you shouldn't, okay? Why have bugs changed? Why have all those older bugs that I just talked about, what's made those go away, and why have things gotten better? Okay, and part of it, of course, is conferences like this and training and awareness, and people have, universities are getting better at teaching the basic stuff. Don't use stir-copy. All the real basic things that we know that are bad are going away, and that's a good thing. So things have gotten better. Better testing, more people are aware of, for example, fuzzing is a good thing. Most people now have heard of that word and generally know what it means. When I first started talking about that years ago, people probably around the 2005 era, people had no idea what that word was. Most people that you would meet had never heard of that term, didn't know what it was. So things have gotten a lot better in that state. On the other hand, the code that is still being written in C and C++ tends to be really complex. So the kernel code and virtualization code and browser code and all that sort of stuff, it's very non-trivial code. So even though a lot of the bug categories of yesteryear are gone, there's new bugs of today because of the pure complexity of the code, okay? So that's kind of where the shift, in my mind anyway, take that with a grain of salt, where and why that's happened. So in terms of, exploitation, that's where people are targeting, right? So if you want to do memory corruption bugs, you need to be targeting fully compiled code. So you might land your exploit against your browser or your Office or your, Adobe Reader or whatever it is. And then of course, you're probably trapped in some low privilege sandbox or whatever. So then you need a kernel exploit to get outside of that, to get full control of the system. Luckily, there's still bugs in both, and they're still written generally in fully compiled code, so you can still do all this kind of good stuff that we're talking about. Okay, it's just a little harder in some cases, but that's okay. So here's some current trends that I pulled out of a recent Microsoft paper, and they show some interesting things that I wanted to highlight. The fact that the simple stack corruptions, like look how many there were in 2007, like 60% of bugs that were exploited were like stack overflows, right? And then 2012, there's not very many of them, right? Why? Because they're a lot harder to exploit. You've got DEP and ASLR and all this kind of stuff, right? And there's not as many because people don't use stir copy anymore, right? They've decided that that's a bad function and they've found something else. So there's a sense that some of those types are going away. On the other hand, if you look at use after free, those are going up, right? Because as people are still going to do exploitation, right? Bad guys or whatever, good guys, I don't know, are still going to do exploitation. So there needs to be a way for that to happen, okay? And so then you just have to transition your tools and techniques to some other form of exploitation, right? That's why you see use after free and type confusion and these other types of bugs on the rise. As some die, some will grow. New techniques. Okay, and how are these newer types of bugs, this use after free and type confusion, which I'll explain if you have never heard of that. This is not a real advanced talk on either one of those two, but I'm going to, basically explain what both are and show an example of each and stuff like that. If you've never heard of those, how are those two bugs categories found? Basically the same way we've always found bugs in fully compiled code, right? Fuzzing, source code auditing, manual reviews, automated tools, iterative approaches. So you're doing some browser fuzzing, you find a crash, and then you go, oh man, I wonder why that happened. I have no idea what this is. You go back and you look through the WebKit source code or whatever, and you go, there's this whole new category bug I didn't even know about. And then so you go back and you retool your fuzzing tools to target that specific category of bug, and then you kind of just keep looping, right? So, and that's basically what people have been doing for more than a decade, right? They've been doing that same thing when they first found format string bugs and Stack Overflow. It's like, whoa, there's this whole crazy category bug. Maybe when we fuzz and put in, semi-random data, we should put in a whole bunch of %ns or %x's, right? There's heuristics that were grown out of the findings and the retooling that took place. Same idea now as there was then. Whoops, went the wrong way. Okay, so first I'll mention kernel bugs, but then basically I'm not going to show examples of them. I'm going to show examples of more of the browser bugs. The bug I wanted to highlight that seemed to be big to me this year anyway, at Black Hat this year, Black Hat USA 2013, was the time of check, time of use. There was a good talk there by some Google researchers that talked a lot about the so-called double fetch, which is a form of the time of check, time of use. And the way the double fetch bug works is the user process tells the kernel, hey, I need you to do something for me, and the kernel says, okay, let me take a copy of your parameters, and then I'll, open a file, or whatever it is that, you asked me to do in the system call. And then, so the time of check is right when it checks to make sure that, some pointer, it dereferences the first value and finds out that the length of it's okay or whatever. But then right before it uses it, you've got some tight loop spinning, because you're trying to do some local privilege escalation, right? You've got some race that you're trying to win on the host. To some tight loop spinning where you're trying to change that value as quickly as you can. And then when it goes to use it again, it didn't actually make a real copy, which is what the problem is, of the user parameters. It checked the length or whatever at first, and then it uses it again in an actual copy or something like that. But by then, things have changed only milliseconds later, okay? So that's a race condition, time of check, time of use, that category of bug has been around forever, but that specific case, the double fetch that really blew up Windows this year, was fairly, that was kind of a, Ron Burgundy, kind of a big deal this year at Black Hat, right? So, and Linux has had its share of issues. It wasn't as vulnerable to that specific issue, but Linux has gotten blown up for years in the kernel, okay? And Mac tends to keep its nose clean, stays out of the press a lot, you don't hear a lot about Mac vulnerabilities, but I know there's probably just as many, or there are issues, okay? They just somehow find a way to kind of keep a squeaky clean image in terms of public vulns that are out there. So I'm not saying that any one of these is worse than another. They've all had their issues in terms of the kernel, okay? So kernel bugs are there. They're probably going to be around for a while. I mentioned that, the code that's there is complex. And one of the complexities, one of the things that's changed in newer code that we really didn't see a lot of in the traditional C code is this whole object lifecycle management, okay? And the thing that's used to do that in modern code is what's called smart pointers. And smart pointers is just a way of keeping track of some data, but we'll show an example of it. I'll explain it in just a second. And the other thing, so that's going to be more of the use after free, and then the other thing is the casting of complex objects, which is the type confusion. So they're somewhat similar, and we'll see how each one of them works and why they're a little different. How am I doing on time? Let me check. I'm doing pretty good. Okay. Okay, so smart pointers, the way things used to be done when you wanted to allocate an object in C++, you would say, I'd have a pointer, new, my object, pointer, do something, and then when I'm done, I personally am in charge of deleting it. So you do the new, you do the delete, you're in charge of the object life cycle, okay? That's kind of how it was. That's how it is in some cases still. The problem is, what if when I do something, there's some exception thrown and that object goes away and that pointer is now null or not valid or whatever, and then when I go to delete it, I've got an issue, right? That's basically a use after free or some sort of object lifecycle issue. So what was come up with is the so-called smart pointers, where you do some smart pointer type. This is off Stack Overflow. This is just ripped right off Stack Overflow, by the way. There's a great write-up that I found there that I pulled out of there, put in here. Good stuff. Some smart type of shared pointer, or smart pointer rather, and then you do something, and then it'll later free it when the time is right, basically. So there's some destruction policy that'll take place. And one of the simplest is what's called scope. So in this case, if you've got my object here that gets allocated, as soon as it goes out of scope, then the pointer is freed, and if you later try to use it, the compiler will tell you, hey, that object's not valid here. So it'll give you some warning that you're trying to do something bad, right? So that's a simple case. A more complex case is the shared smart pointer, which basically does reference counting, okay? And I'm not really going to explain a lot about it or anything like that, but to make a long story short, there's some reference or count of how many instances of that object there are, and every time one's destroyed, that count's decremented, and when the count's 0, then that object's destroyed and freed, okay? So there's some object lifecycle management. And we see that happening here, where when it goes out of scope, P2 is destroyed, and then finally P1's destroyed down here. Okay. Well, there could be some issues with that, where you may have some dangling pointer or some circular reference, and there's other types as well, the auto pointer, which I'm not really going to go a lot into right now. I just wanted to make you aware that there's a lot of different utilities out there for doing object lifecycle management. Okay, so last third of the talk, I want to talk about the two, I guess, in my mind anyway, the most prevalent bugs out there in modern C++ code, the use after free and the type confusion. So first we'll talk about use after free. What is it exactly? How does it work? Why is it called what it is? So what happens is you have some object A, there's some memory associated with it, and then for whatever reason, for better or worse, valid or not, it goes away. So somehow it's freed, but maybe, just maybe, you've maintained a reference to that when you shouldn't have. And that's kind of what a use after free is, right? You've got some reference still. And the attacker has time to slip something in there through heap spring or through some other tricky technique. They're able to somehow fill the place in memory where that pointer was pointing to, but now with attacker data. And then when it gets used again, then you've got one of these three primitives, either read, write, or execute, is now available to an attacker, right? They can either hijack the execution of the program, or they can read some data or write something somewhere in memory that they shouldn't be able to. In fact, they'll probably need all three, right? And against modern protections, they probably need some sort of memory leak to leak the base address of some DLL so that they can create a ROP chain so that they can finally hijack execution and get their payload to run. They'll probably need some combination of primitives to actually land an attack. Okay, so where do we see these UAFs showing up? Browsers, Chrome, Safari, Internet Explorer, Firefox, Opera. If you actually use Opera, I don't know what to tell you, other than you probably shouldn't, but they're out there in all of these. So none of the browsers are immune to this. There's not one browser that sort of stands alone that doesn't have issues, right? They all have this issue. And you can find references to every one. You can look around for different CVs and figure out that, this one had an issue with this use after free here and it looked like this. This one had a use after free here and it looked like that. The one we're going to look at is one from Chrome that was fixed in 2011. Mainly because it's just a good example. It's easy to understand. It's easy to look at and see. There's not a lot of code you have to show on the screen to try to understand this particular example. What happens is, I don't know if you can see that very well or not. It looks fuzzy to me up here, which means it probably looks fuzzy back there. But you have some reference pointer at the top, T, which is generally good. We generally want to use smart pointers if we can, as opposed to native pointers, if you've got the right policies in place for your code base. And there's some stuff done in this function called setOuterText from html_element.cpp. But then down here is where the problem lies. We allocate this new object called textNext equals static cast text star next. And that is a native pointer. There's no reference pointer being done on that. And then this function T, append data text next, is called. And the reason these types of bugs show up so much in browsers is because you have this disconnect between you've got the C++ running on the process itself, and then you've got the JavaScript running in this other world that can be influenced by a malicious attacker, right? You visit a web page, the web page can do all kinds of fun stuff in JavaScript. And one of the things it can do inside this JavaScript, it can actually get that text next to go away. It can get that to be freed. But we don't see that. That's the bad part of this bug, right? We can't see that by looking at this code unless you just happen to know that. There's no way from just looking at the raw code here to know that append data goes off the JavaScript and could free that unless you just happen to know that, right? So they're pretty hard to spot in static manual review, right? You might not see that this is a problem. And then next you see text next is removed right here. It doesn't matter if it was removed or added or whatever. The fact is you're doing a use after free. You're calling some function pointer when it might not be no longer, that object may no longer be pointing to what you think is there. It could be attacker controlled data at this point, right? So that's kind of where the naughtiness takes place. So non-reference pointer defined, that could be bad. So what do you have to do to fix that? All you have to really do to fix that, the use after free, is make sure it doesn't get used after it's freed, basically. It's kind of, the fix for a lot of these bugs is not all that complex in many cases. What they did was kind of change this whole set outer element function. They changed it to go to some other merge with next text node. And they use a reference pointer inside of here, and on top of that, they check to make sure it's valid, that it hasn't been removed, and then they do whatever it is they wanted to do, this text next remove. Okay, so they just do some more sanitization, basically, some more input checking to make sure that we're dealing with an object that's still valid. Okay, so the fix for that is not necessarily insanely difficult. It's just that spotting those bugs can be a bit challenging. Although I have to assume that automated static analysis tools will eventually get to a point where they can find them, right? Because it took a while for automated static analysis source code auditing tools to be able to find buffer overflows and all the kinds of things they can find now. So I'm assuming eventually they'll catch up to be able to find use after free and type confusion and stuff like that. So there's got to be heuristics that you can put in place to sort of find these in an automated fashion without having to try to manually hunt for every one of them. Okay, so that was use after free. What about type confusion? So type confusion is basically where you have some data. In this case, we're supposed to be treating some data as a struct T, but maybe somehow accidentally we treat it as a struct C, or a struct Z. And why is that bad? Well, we'll look at a case where that's bad. So in this case, we wanted it to be two D words, an int and a pointer, and somehow it accidentally gets treated as a uint and a short and some object in some other uint short, so uint 16. So what? Why is that a big deal? Why does it matter that we somehow cast that data into some other format that it shouldn't have been? Because maybe if that was user-controlled data or something, maybe this object is now going to get dereferenced, or we can somehow have one of our 3 exploit primitives read, write, execute based out of that. Where do we see type confusion showing up? Kind of similar to the use after freeze, similar environments, basically complex environments like browsers and Java, where you have some virtual machine operating on bytecode. There's all kinds of translations going on from one type to the next. IPC interfaces where you're sending complex objects over some pipe and they get recast or rechecked or something on the other side of the pipe. Those are the kind of areas where you can expect to find these things. And the things to look out for are the static and the reinterpret cast. You see that those can be potentially naughty a lot, although they show up a lot in valid places too, so you can't just do a grep for a static cast and think that you're going to find every type confusion, because it may be perfectly fine in many cases. So what's the example we're going to look at here? I'm going to look at the WebKit example, CV 2013. And there was a really good write-up by this MWR Info Security organization on this particular bug, and I'm not going to do really justice to this bug. I'm not going to go into all the exploit details like they do on their blog and really dig into it. I just want to show the code, and so we can have a general idea of what a type confusion is. Okay, so the basic idea is that there's some SVG document that you can supply, okay, as a malicious website or whatever, and at some point they do this context element, tree scope, get element by ID on some portion of the document that you supplied on some string, and they assume that the return value, the code, the WebKit code assumes that it's a SVG element pointer, and they static cast it as that. Okay, but it turns out that in some cases you can supply a string with a certain tag that'll cause that element that's returned not to actually be an SVG element, so that when they cast it and use it as an SVG element, they think they're using an object of one type, but it's actually an object of a different type. And the important thing is, it's a type that's shorter. It's actually what gets returned is some other type called HTML unknown element. And without going into all the details of what, I'm not sure, this isn't the valid layout of each type, but the point I want to show is that the one that they think is there is actually longer than the one that gets created, so that you can call methods F and G and access data in actual memory outside of the scope of the object that was created by the application, such that you can groom the heap in a way that you can do all kinds of interesting things. So the actual exploit for this is, creative and convoluted and multi-stepped and quite wonderful in many ways if you enjoy the art of exploitation. First they leak a pointer, and then they calculate the base address of a DLL, and then they read the DLL and dynamically find the gadgets they need and create their rob chain on the fly, and they win with their lovely exploit. Okay? Which is all kinds of big fun, right? From an exploitation standpoint, it's like, wow, you could spend months researching and making an exploit against something like that go. But it turns out the fix is really, if you knew that this problem existed, which, right, that's always the problem, but you probably, obviously they didn't originally, but once they found out this problem, the fix is not terribly complex. So if you have type confusion, all you have to really do to fix type confusion is check the type to make sure that you're not confused about it anymore, right? So that it seems like, oh, okay, that makes sense. So the type that you get back, you just have to make sure that it is an SVG element, and if it's not, you bail out, and if it is, then you do whatever code that you were going to do, which was causing the bug in the first place. Okay, so the fix is pretty straightforward. No cast and some better checking, type checking. Okay, so that is pretty much all I had to share with you guys today. I hope you enjoyed that. In conclusion, we definitely need to go beyond DEP and ASLR. Okay, yeah, I'm wrapping up. all the kinds of modern day protections that we have out there that, mark memory as non-executable and randomize the address of base, DLLs and all that kind of stuff. Those are all good protections that make exploitation a lot harder, but the fact is exploitation is still taking place, okay? And in particular, Windows 8 has got even more, new protections, VT-Guard, Force ASLR, high entropy heaps, anti-ROP that came from the whole Emmett Blue Hat Prize thing. If only, this is my pitch, there were some company that could stand up and make a difference and come up with some security through isolation so we wouldn't have to fight this cat and mouse game of security. That's kind of a pitch that you can hear more about if you want to learn about our company, Bromium. In fact, my co-worker and chief security architect Rahul is in the room here. He's going to be giving a talk tomorrow. I highly recommend that you guys go to his talk. He's given a great talk on sandbox escaping. Be good. So that's what we need to do to have better state of security. We either need to write perfect code by using the 10,000 steps so that bugs never show up in code so everything's perfect, or there needs to be some different approach to security. So that's kind of where I'll leave it today. If you want to get a hold of me, I've got my website and Twitter and LinkedIn and our labs where we do some pretty cool blogs, I think. So that's it. Hope you enjoyed. Looks like there's one question.
I see a lot of null dereference a lot, like I'm getting these reports back saying, oh, you have this null dereference problem. Do you know what that is?
Yeah, so the question is, what is a null dereference? He's seeing those a lot. That's basically where you try to operate on some pointer which for whatever reason became null. It got invalidated. Maybe it got freed, maybe it got overwritten, maybe it was never allocated and they tried to use it in a constructor or something. I don't know specifically why those null pointers are happening, but I would definitely look into them because the jury's out. Some people thought for a long time they weren't exploitable, and then it turned out there were cases where they actually were. So I would be somewhat concerned about if you're getting a lot of those. Question back here. I'm sorry, I didn't understand a word of that. Oh, the diff tool that I showed in the presentation? That was a tool called SCI Understand. It's a really good tool for diffing code and auditing code in general, I think. I like the tool a lot. Any other questions? Back there.
What was the IHP stack mitigation between Windows 8 you're talking about?
Oh, yeah, from Windows 8 there's a new, I don't know, was it high entropy stack? I think it was high entropy heap, right? That's just basically forcing the allocations to be more random than they were. Yeah, so the problem was there was some attempt to make, heap allocations randomized, but it wasn't that good. So if you're doing some heap spraying and all the chunks line up in a row, it's easier to groom the heap. But if they're all over in memory, it's a lot harder to groom the heap in terms of exploitation. So, any other questions? All right. Have fun. Have a good con. We'll see you around.